Hi, my name is Nirnimesh Ghose, and I'm from Department of Electrical and Computer Engineering, University of Arizona. And I'm here to present our work, Helper-enabled in-band device peering resistant to signal cancellation. Nowadays, we are all connected to multiple number of devices wirelessly, such as child and elder monitoring, health monitoring, fitness tracking, nutrition tracking, smart lighting, temperature control, home surveillance, even smart cars. The main idea here is that these all devices are collecting very sensitive data, such as the user behavior, whereabouts, state, and other information, and it's important to protect the security of all these information. So how do we secure the information flow to protect the plethora of the collected sensitive data? We need some help. So our work is based on the classic trust establishment problem, where Alice meets Bob for the first time, and Alice and Bob does not know each other, but they are meeting in presence of an adversary, Mallory. So they need to do two things. First, they need to authenticate the identity of each other. And secondly, they need to verify the integrity of communication, through which they can generate a common secret key, which can be used to protect the security of the information. So in the problem setup for our work is that a legitimate device is trying to pair with the wireless hub in presence of Mallory, and hub needs to verify the authenticity of D, because these do not share any prior secrets. And secondly, at the end of the peering protocol, the device and the hub needs to have a common shared key, KDA. The biggest challenge for this problem is that the most of these new devices, such as the smart devices, does not have a interface such as keyboard. As we can see here, a pacemaker which will be implanted inside the body does not have a keyboard or any interface to enter any keys or password. So the threat model we use for our work is that the adversary is trying to pair as a rogue device to the hub, or it is trying to pair with the device and asking it to join and acting as a rogue hub. Adversary can perform this by doing a man-in-the-middle attack over wireless. To do the man-in-the-middle attack over wireless, the adversary needs to be aware of the D2A channel, and this is relatively stable and predictable for indoor environment. Adversary needs to be aware of the channel to the device and the hub, which it can compute from the preambles. Adversary needs to synchronize with D, that it can do with the preambles of the transmission. And using these, the adversary can now perform an overshadowing attack or a signal cancellation attack to do the man-in-the-middle attack. So the existing solutions for building trust establishment include manually entering password to the devices, but this requires having advanced interfaces such as a keyboard or a monitor or some channel to do that, but most of the existing smart devices may or may not have this thing. Secondly, the idea is to preload the device with a default password, but the problem is that many manufacturers are opting to preload with the same default password to multiple devices, which has led to the recent Mirai botnet attack, where a number of IoTs, those were preloaded with the same default password, was leaked, and they were compromised to orchestrate the biggest DDoS attack last year. Or we can execute a Diffie-Hellman key exchange, but this is vulnerable to man-in-the-middle attack, as A and D cannot verify the integrity of the key primitives exchanged. Third, there are out-of-bound solutions proposed, such as the verification using ambient light, ambient sound, or LEDs, but these requires interfaces such as microphones or some optical sensors, and these might not always be present. And then there are a few non-cryptographic verification techniques proposed that uses hard-to-forge physical layer properties, but these require specialized hardwares, so it is not that practical to implement them. Third, the best technique we feel is the in-band verification technique, which only requires a common radio interface and which is present for all the devices that are wirelessly connected to each other. Therefore, in this work, we focus on to develop an in-band pairing protocol. The basic idea of in-band verification techniques that has been proposed in the past is that suppose the device now wants to transmit a message MD over the wireless channel, it can encode it with Manchester coding and on-off keying and transmit it over the wireless channel. But these all works assume that signal cancellation is not possible due to the rich scattering environment, or it occurs with limited probability. But if a signal cancellation attack is possible, then a Mallory who wants to inject its own signal, its own message instead of the message from device D, can actually cancel the on-off keyed message from the device T and transmit its own on-off keyed message. So is the infeasibility of signal cancellation assumption does not always hold, because in indoor environment the channels are fairly stable and those can be predicted. And in 2011, Popper et al. Demonstrated effective relay signal cancellation attack using a pair of directional antennas. So now understanding how this cancellation works is that suppose for a particular symbol, the constellation point received from the device is represented by the green line, and the constellation. So if Mallory transmits a constellation point for that symbol, and it is received exact copy of the constellation point received from D, but shifted by pi, then the superimposed signal will be reduced to the noise floor, thus causing cancellation of that particular symbol. And suppose if Mallory wants to do cancellation and injection simultaneously, then it has to calculate equivalent constellation point such that the superimposed signal is the constellation point which is intended by Mallory to be received at the hub. So we performed few experiments on USRP platform to see the feasibility of these attacks, and as you can see from the plot on right hand side, that the cancellation is almost possible 90%, and the cancellation and insertion more than 90% when we use BPSK modulated symbols. The x-axis here is the channel estimation frequency of from Mallory to device and Mallory to the hub. We repeated the experiment for the QPSK modulated symbol, and we saw similar trends in cancellation. So our contribution in this work is that we construct an in-band message integrity verification primitive for devices that do not share any secrets, and then we use this primitive to complement the Diffie-Hellman key agreement protocol, and we proposed a HELP, which is the first protocol resistant to man-in-the-middle attacks based on signal cancellation. Then we analyzed the security and show it's a negligible, the success probability is a negligible function even with perfect signal cancellation. And finally, we implemented HELP on USRP test beds to validate the effectiveness of the primitive in detecting message injection, and also we determined the adversary's diminishing success in pairing rogue devices. So how does help work? It's under the similar setting of in-band verification. Now the device is transmitting message MD to A, and it is transmitting in Manchester coded on-off keying. But now we introduced a helper H, which and here we assume that the helper H is already paired with the hub, so it shares an authenticated channel. And this pairing is a one-time process, as the same helper can be used over and over to pair multiple devices. So the hub here injects random slots on random locations, and the signal received at the hub the helper will inject the random slots, and the signal received at the hub is the superposition of these two signals. So now when the adversary Mallory is trying to inject its own signal, it will unknowingly cancel out the slots on which the helper injected signals, and the hub, as it is expecting on slots on those particular slots, so it will know that a cancellation attack has taken place, and it will not accept the message from Mallory. So we use this primitive to propose a device pairing protocol, so in which now we transmit the hash of the message MD and the MD message together in Manchester coded on-off keying. We transmit the hash first for two reasons. First, the hash will be not predictable for Mallory, and secondly, now to change message MD, the Mallory will be forced to change both hash and MD. Thus it will have multiple onslaughts to cancel. And this message is sent with the superposition of helpers onslaughts. So, and then the helper will send the location, the vector S is the location on which the helper has injected onslaughts, which is sent by the authenticated channel, and the hub will receive these and verify that it received onslaughts on those particular locations, and then it will clean up the superposed signal and extract MD. And finally, the hub will reply with its message, and at the end of the protocol, both entities can generate a common key, KDA. The success probability for an adversary so that the hub accepts its message forgery is based on this, and where Pi is the probability of inferring helper's activity during one slot, and the cardinality of vector S is the number of helpers on slot. So from the plot, we observed that delta is a negligible function of number of helpers on slot. And now we see how an adversary can perform a man-in-the-middle attack for the device pairing protocol. So now when the device is transmitting its message MD, which is superposed with the message MH from the helper, the adversary will cancel out and it will inject its own message MM. And so for the uplink, when the helper sends out the vector S, the verification that the hub received all onslaughts on vector S will fail, and hence the hub will detect the presence of Mallory. And for the downlink, when the hub is transmitting MA, the Mallory can cancel and inject its own MM. But here we see that the positions on which the onslaught are present are sent through an authenticated encrypted channel. So the adversary will not be able to extract S. Therefore, it will not be able to clean up the superposed message, and it will fail to extract MD. Therefore, the keys that are denoted in red will not be generated at the end of the protocol. Hence, adversary is not successful to do man-in-the-middle attack for the uplink or pair as a rogue device, or it is not able to do it in the downlink where it will force D to pair with a rogue hub. The probability of the downlink direction is relatively different from the uplink, because here the pi prime is different, as this attack can be done offline, while the one on uplink requires an online probability of inferring helper signal. And also S prime, the vector is different, because this is the vector only on during the transmission of the message, not the hash. But we see that this function is also a negligible function of number of helpers on slot. So the success of adversary depends on how well it can infer the probability of helpers activity during one slot. So next we study that how the adversary's capability of identifying helpers on slot. The adversary could employ several physical layer characteristics, such as frequency offset, channel impulse response, IQ origin offset, transient radio state, angle of arrival for incoming signal, received signal strength, and time offset. But for this, we are looking into the techniques that can be used only for an online attack and does not require much computation. So we look into the received signal strength and time offset. For this, we performed experiments on USRP platform, where we placed a device on top of a helper and placed the adversary Mallory at a distance from it. And the blue signal is the signal transmitted from the device, and the green signal is the signal transmitted from the helper. So we repeated this experiment for different topologies. For this topology, the helper is directly placed on top of the device, and both helper and the device is transmitting fixed powers. And from this plot, we can see that when both device and helper are transmitting, or when both device and helper are not transmitting, Mallory is able to detect that with full certainty, while if the device or the helper are transmitting, at that point Mallory the probability of inference is equivalent to a random guess. Then we repeated this experiment by varying the transmit power from device and the helper, and we see the probability of inference is almost equivalent to our previous experiment. Then we see how much distant can we put the device and helper from each other. So we increased the distance between the device and helper, but kept it equidistant from Mallory and transmitted fixed power. And we observed that we still get the similar trends as previous experiment. And now when we move the helper towards Mallory and transmit a fixed power, we see that here now the Mallory is able to infer helpers on slot with almost certainty. So to mitigate this problem, we propose to transmit random powers from device and helper. And when we do that, we see the probability of inference trend is almost equivalent when the device and helper are placed on top of each other. Next, we look into helper detection based on time. Like these two device entities, helper and device, are synchronized, but perfect synchronization cannot be obtained. So there may be missynchronization due to clock drifts or path delays. So in this, we see the helper is always faster or slower, and Mallory can use these to detect presence of helper signal. So to mitigate this problem, we propose to randomize the starting time of each slot such that the helper is sometimes faster or sometimes slower. We implemented this on USRP platform, and we see the number of slots on which device or helper is faster is equivalent to the probability of the occurrence of that is equivalent to random guess. And finally, we did the protocol evaluation where we placed the device and helper on top of each other. And to implement signal cancellation, we put two receivers such that receiver 1 and receiver 2 receive same signal but shifted by pi. And then we added these signals on MATLAB to implement signal cancellation. And from these, the graph on the left shows the results without the results of Diffie-Hellman without using help, and on the right is the results when we use help with Diffie-Hellman. And here PC is the probability of signal cancellation. So we can see when we use help, and even if the probability of signal cancellation is equal to 1, the success probability for adversary is a decreasing function when we increase the number of helpers on slot. And finally, concluding this talk, we proposed a new physical layer integrity protection scheme that is resistant against signal cancellation. Our protocol is aimed to alleviate the device peering problem from IoT devices that may not have appropriate interfaces for entering cryptographic primitive. And then we used help to complement the Diffie-Hellman key agreement protocol that is now resistant against man-in-the-middle attack without requiring an authenticated channel between the device and the hub. And for the future, we propose to investigate on MITM resistant in-band peering technique, but that does not rely on on-off keying so that it can be compatible with commercial off-the-shelf devices. Thank you.
Okay, we have already a question.
Abdul from Carleton University. So regarding signal cancellation, did you test what will happen if the attacker kind of floods the network with signals instead of sending one signal to hijack the channel?
Can you repeat the question?
If the attacker floods the network with the signals for conducting the man-in-the-middle as opposed to like sending one signal which gets cancelled by the helper?
That is more a denial of service attack, or it can be an overshadowing attack. So this will still detect that attack, like if it does not cancel it. Because when it does that, the helper signals will be suppressed. And it is more of a denial of service attack, which we did not study in this work.
But I didn't mean in the sense of flooding the network to the point of not making the band usable. I just meant even flooding like intermittently so that it makes sure that if a helper sends the canceling signal, the attacker signal will override it at some time.
That will happen if the attacker can send it with higher power, right, to do the overshadowing attack. If both signals are sent on same power, then because it uses on Manchester coded on-off keying, it should have equal number of ones and equal number of zeros. And if all the signals are superimposed, that will not happen, and it can be still detected at the hub.
Okay. So the second question, so you mentioned multiple helpers. Have you also tested multiple attackers?
We use only one helper.
Oh, at the end you said a helper with multiple slots or multiple slot helpers? I didn't get.
We, in all the experiments, use one helper and...
Okay, so my question is, what will happen if the attacker controls more than one device in the network? Do you think this will have any effects on...
So we have an assumption that the attacker does not have any physical access to any of the devices, okay, even the legitimate device, because when you start the protocol is started by switching on the legitimate device such that the attacker cannot send a request to join.
Okay.
We have described it more in the paper.
Other questions? I have a question. So,
yes.
And this is more of in your future work you mentioned to be able to work with, sort of COTS devices. Mm-hmm. But this seems motivated by IoT. We have a lot of IoT devices. So have you seen or have you worked on making this attack, the man-in-the-middle attack, work to demonstrate that this is actually a problem with current devices?
We can implement this, like on this work, we implemented using USRP testbeds, the actual man-in-the-middle attack, even for the on-off keying, because all the previous InBand protocols are proposed using on-off keying messages, most of them. So we try to target them and to see if the man-in-the-middle attack is actually possible. So we did implement it using USRP testbeds, but we did not use any COTS device for this paper.
Okay. All right. Let's thank the speaker again.